Hey everyone, it's been a while. In fact, it's been 4 years, so I thought what would be better than putting out part 4 of the Regolith devlog. I've been working on this project in my spare time, and I thought it would be fun to get back into making these videos. So let's get right into it. I want to talk about how this project transformed over the last few years, the new tech, and the next steps. Alright, so what's staying? What was like the cool part about Regolith? The cool part was that all of the health was cell-based. So there's cells in the middle of you that are orange, and those are kind of like your health. And all of like the AI and stuff is connected to those pixels. So wherever those pixels go, that's going to be like you, basically, and that's going to be the enemy. And then there's all these other pixels that are just kind of like shell pixels, I guess, that can get blasted off of them. So as you can see here, you can go and you're fighting these enemies, and they're exploding, and your bits are flying off of you. And if you get these like little health things, your bits come back. So after part 3, I began development on the splitting code, but it breaks my heart, but the falling sand mechanics had to get cut from the game. This was mainly due to one major problem, which was that to move sprites around and have them actually interact with the falling sand, you had to paste them into some sort of state array. And so that was like incredibly slow and annoying, because you'd think like, oh, maybe you could like use the GPU to rasterize them, but that sucks because then you have to like block the whole pipeline and get back a frame from like 2 frames ago, because the GPU's off doing its own thing. And once you're like, your gameplay code is trying to request frames from the GPU, everything's stalled out and it sucks. So you have to kind of come up with this like software rasterizer, which that also sucks because now you're doing software rasterization. And so it kind of limits the size of the sprites. And also, if you then wanted to sort of render one thing and have the sprite on this in the cell state be different, I didn't really like the idea that in a game about removing pixels from sprites, that if you removed a pixel, it wouldn't actually be connected to the pixel that you're looking at. So I kind of made the hard decision to take all the falling sand stuff away. I had to replace the sand world with just a more normal kind of like quad renderer, and each sprite being its own sort of game object. Also, in the meantime, I had played Spore again, and I forgot how, everybody kind of shits on the cell stage, but it's actually kind of fun if you go back and play it, because it only takes like 5 or 10 minutes, and there's some pretty cool encounters in it where I like how it starts, and there's these enemies in the background that are so big that you can only kind of see like half of them at a time in the camera. And also, as you get bigger, there's these like food globules and these little like cellulose structured things that you can't get through, that are also so big that you can't really see the entire structure in the camera. And I thought it would be really cool to try to recreate this in Regolith, because I really like the idea of kind of rolling up on some sort of asteroid or some sort of enemy, and it's like so big that you're shooting away at it and bits are coming off of it, but you can't actually see the entire thing in the camera. So I tried to create really big sprites in the old version, but because all of the algorithms were n squared, it made it really slow. And every single time you would shoot a sprite, there'd be a big lag spike, and it was even worse when you were splitting them. So I was kind of looking at these, and I was always wondering like if there was a way that you could try to detect cuts, but only by scanning local areas. And I sort of had this idea that if you split the sprites into chunks, you could use some sort of graph search to try to figure out where the cuts were. So that inspired a new algorithm that I have come up with that I want to show you. The algorithm I started with was basically just LeetCode problem 200. The idea is that if we want to get a list of regions, we start with a normal flood fill. However, we keep its visited state around and share it with flood fills on each pixel. The pixels which have already been visited get skipped. After doing this, we have marked all the regions and can split off all but the largest one. This works alright, but as an n-squared approach, so once the sprites grow too large, it causes a lag spike every time a pixel is removed. The main issue is that small local changes cause a rescan of the entire sprite. I solved this by splitting the sprites into chunks and coming up with an extension of the idea of these flood fills to handle the chunk boundaries. The core concept is because we don't want to cut out the largest section, our scan should focus on exiting once we have identified everything but it. So let's look at how this works. We start like before, but now instead of flood filling the entire sprite, we only flood fill the chunks that are dirty. This gives us a list of regions with a unique ID. So now we can explore from the regions into neighboring chunks, but what happens if another region has already explored those pixels? Well, we can use an algorithm called union finds to combine the regions by ID. This is stored using a separate data structure, so we don't need to write the new ID to all the state cells, because that would be slow. The key to making this search efficient is spending as little time on the largest region as possible. To do this, I partition the searches by ID and keep track of the total number of cells they have seen. This list of searches is then stored in a priority queue, and the pixel count is used as the rank. The final optimization is keeping track of the number of searches still remaining per region ID. We can use this as the exit condition, because once there is only a single region left searching, that must be the root, and we don't care about it. This is nice because with one check we can cover the case where there is no cut,
A cut has looped back on itself?
or there are cuts but they have been fully searched and are ready to be split. The output ends up as a list of regions which can be combined into a big list per unique ID and then used to cut out sections of the sprite. Let's look at it in action. Here we can load in a huge sprite and it'll give each region a random color. If we shoot cells out of it, only 1 or 2 chunks need to be checked with each hit. And if we cut out a large section, the search remains local to the cut location. So now I can load in a sprites as big as I could ever really want for Regolith. So now we can split large sprites, but how are we going to bump them into each other? In the old version of the game, I used the method described in the Noite Tech Talk, where we can scan a sprite using marching squares, and then do some cleanup, and turn that into a triangle mesh and give it to Box2D. However, this runs into the same problem as the splitting code, because now whenever anything local changes, we need to change the global info about the sprite, in this case the list of colliders. I came across a YouTube video by another fellow making a voxel-based game named Douglas, who pointed out a technique developed by the teardown developer to use voxel data directly as the collider. So let's look at how this method works. The name of the game is reducing the amount of checks which need to happen and making it as multi-thread friendly as possible. To reduce the number of checks, we reach for a series of broad phases, from the transforms of the sprites, to the chunks in the sprites, to the cells in the chunks. I want to start with the cell level because it's a pre-processing step. We want to identify the boundary of each object because that's the only thing which will be colliding. In the teardown talk, they explain an optimization where they need to collide the edges and corners of one sprite, but only the corners of the other. So we can classify each pixel as a corner, edge, or interior. Okay, so now we have classified all the cells, we can look at the simplest broad phase, checking if the transforms of the game objects will overlap this frame. To do this, we can turn them into a bounding box, expand it by the velocity, and throw them into a spatial tree. This lets us get overlaps in nlogn time. Now that we have the pairs of sprites to overlap, we can use another broad phase to select a subset of the chunks to actually test. Finally, each edge and corner cell can be stepped through the world to test if it will hit anything. For each sprite, we keep track of the contacts and their times, and then step the sprites forward to the soonest contact and apply impulses. This method is actually faster than I expected, and is very friendly to multi-thread, so I spent some more time looking at Tracy to optimize it until it was fast enough to handle many shapes at once. I probably will need to come back to this in the future to make it more correct and also faster, but I think for now it's fine. So let's see some results. There are some bugs in the collisions, and sometimes sprites get lodged into each other. However, I think that if you're going to have bugs, they should be fun. And in this case, in a game about blowing everything up, at least there's some fun encounters where you need to escape being trapped. For some reason, nothing ever seems to look too jittery when broken, so I think it's good enough for me. And that's all I got for today, fellas. I hope to make more of these videos, hopefully not in 4 years, because I think it's time to wrap up this game. I want to explore other stuff besides just voxel mechanics for my whole life. So the next steps that need to happen is re-adding the sound and music that me and my brother had made, creating some interesting encounters, and I want to test out making sort of like a big cavernous level thing out of the big sprites and see how that's going to work. So I'll probably have another video in like 2 or 3 weeks or something, so stay tuned. Bye-bye.